Hello, and welcome to a lecture on the geometrical theory of diffraction. My name is Steve Ellingson. So first, a bit of context. In previous lectures, we've been discussing the problem of analyzing reflector antenna systems, and we've avoided the problem of rim diffraction. We've done that by limiting our focus to the main lobe and the first few side lobes. Now we know that the methods that we've used, geometrical optics, aperture integration, and physical optics, surface integration, fail, although gracefully, with increasing angular distance from the main lobe. So even though we have these techniques, and they do a good job with the main lobe and the first few side lobes, and give us good estimates of directivity if the directivity is high, they don't work for the far side lobes. So you could say, well, if you want the far outside lobes, why not use a numerically exact method, such as the method of moments, finite difference time domain, and so on? Well, reflectors are typically electrically large, and solutions potentially involve very large computational burden, not only for the very first iteration, but if you're doing a design, and the design requires iterating design parameters over and over, this can be prohibitively computationally expensive to do. The second reason why we're not terribly interested in falling back on these types of methods, full wave methods, is because such methods typically do not provide insight that is needed to guide design. In other words, when a design doesn't work the way you want it to, and you'd like to adjust some parameter to get you closer to what you want, it's difficult to see how that happens in these methods. What happens in full wave methods is you simply provide the design parameters and you get out an answer. What we'd really like are methods that tell us something about the individual effects of changing individual parameters without having to repeat the analysis every time. And that's what ray optical solutions do for us. And in particular, that's what GTD, the geometrical theory of diffraction, gives us. Now, the reason that GeoAI and physical optics surface integration do poorly for the far side lobes is that those features depend to a large extent on diffraction from the rim. Now, could we calculate just that? Well, obviously we can, and the answer is GTD. And we'll find out in this lecture how to do GTD, but we'll also find it has some limitations. So this is really a two-part lecture. In this lecture, we're talking about GTD. We'll see that it works, except with some limitations that are potentially difficult to live with. And then we'll see how to do the final fixes using UTD, which will be the subject of a future lecture. So, overview of this lecture. First, I'll introduce an equivalent currents paradigm for edge diffraction. Now, I recommend that you read this document, An Introduction to GTD Edge Diffraction via Equivalent Currents, before attempting this lecture. This document is something that I've written up to try to connect the idea of equivalent currents, which you are hopefully already familiar with, to the idea of GTD. And I think if you read this and you see how GTD comes about in that manner, you'll find a lot of this material easier to absorb. In any event, we'll end up with stationary phase points, as we did in physical optics when we went from physical optics to geometrical optics. And those stationary phase points, we'll see, will give rise to a principle known as the law of edge diffraction, which tells us how to reduce an edge to just a few contributions along the edge that are important to the diffracted fields. Then we'll finally get to it, the formulation of the GTD diffracted field, the equations that tell us how to calculate it. Then we'll do an example. The particular example will be diffraction from a half plane, a very common but important example. We'll find that GTD works, albeit with some limitations, as I promised you on the previous slide. And this will provide the motivation for replacing the GTD diffraction coefficients with UTD versions in a future lecture. And then a few concluding remarks just to summarize. Okay, the equivalent currents paradigm. So for the main lobe and first few side lobes, we were able to come up with equivalent currents that in free space radiate the same field that is reflected by the reflector. I mean, that was the whole idea in geometrical optics aperture integration. and also to a large extent physical optics. The same source gives rise to energy in the form of rays, as we think about it, that strike the rim and diffract. And that diffraction goes in all kinds of directions. And that's how we get far side lobes. So it gives rise to the question, can we find equivalent currents that, in free space, radiate the same field as the field that's diffracted by the reflector rim? This seems like the natural question to ask, given our experience with the reflection mechanism. Well, the answer is sort of. We can do it, but it's difficult to do it well. A better thing to have here would be a geometrical optics-like paradigm, and that's what GTD is. So we really want to get here to the geometrical optics approach, or the geometrical optics-like approach, but the equivalent currents paradigm aids in understanding, especially this issue of diffraction points and how to select them. So let's follow that route just for a moment. So here's the equivalent currents paradigm for rim diffraction. We have a reflector, which I've shown as a dashed line here, and then currents flowing along the rim, the usual J's and M's, electric and magnetic currents respectively. And at each point on the rim, we define this quantity L hat. And L hat is the edge tangent. So L hat is always the tangent to the edge. Now we have a source. The source provides energy, and that energy strikes the rim. The distance between the source and the point of diffraction is S super I. The unit vector, that is the direction along which the energy propagates to reach the diffraction point, is in the direction SI hat. And then we go off to a field point. The field point is a distance S super D from the point of diffraction in a direction S hat super D. Now the stationary phase points can be determined in the following way. We have this function gamma, which is a path length parameter. In fact, here it is right here. Gamma is equal to the sum of S super I, the distance from the source to the rim, and S super D, the distance from the rim to the field point. There's a minus sign here. It comes from the analysis in the document that I referred to earlier. The stationary phase points, that is the points where we expect the stationary phase mechanism to apply, those points are given as solutions to this equation. So we take the derivative of path length and we set equal to 0. So the stationary phase points are the points where the first derivative of path length with respect to arc length is equal to 0. Now, just as GO can be viewed as PO, reduced to contributions by stationary phase points, GTD can be viewed as a reduction of the line integral that I'm alluding to here to the sum of a discrete number of contributions. So stationary phase analysis is all about reducing integrals to a discrete number of contributions and thereby avoiding the integration. It turns out that the first derivative of that distance from the source to the rim is equal to a geometrical quantity, specifically minus S super I hat, dotted into the edge tangent. And similarly, the first derivative with respect to arc length of the distance from the point of diffraction to the field point is plus S hat super D, dotted into the same edge tangent. Now these results follow from the theory of differential geometry. It's a relatively simple problem in differential geometry. And again, the separate reference can walk you through that. In any event, we make that substitution. We would like this expression to be 0. In other words, the derivative of path length to be 0. We now have geometrical descriptions for the quantities here and here. So now we see that we have this property that the stationary phase points should be those points where S hat super I dotted into the edge tangent equals S hat super D dotted into the edge tangent. And we refer to that as the law of edge diffraction. If you reflect on this for just a moment, you'll see something remarkable about this. It's analogous to Snell's law for reflection. Snell's law for reflection, recall, says that angle of reflection equals angle of incidence. Well, dot products are angles, and so this appears to be saying that the angle of diffraction relative to the edge tangent is equal to the angle of incidence relative to the edge tangent. So here's a picture of what's going on. We see that edge diffraction is a little bit different from reflection, but there's an underlying principle that remains the same, namely that these angles are preserved. A single incident ray gives rise not to a single ray as it does in reflection, but rather to a cone of diffracted rays which all share the same angle. So here is the angle of incidence. On diffraction, we get the same angle, but we generate a cone of rays. Now remember, this cone is simply the result of this one point, a stationary phase point, and the cone, of course, will change as the stationary phase point changes. What about axisymmetric reflectors specifically? An axisymmetric reflector being a reflector which is circular and has rotational symmetry around the axis. Well, for an axisymmetric reflector which is fed from the focus, and this is important, it's fed from the focus, we'll always have exactly 2 points of diffraction for any field point which is not on the axis of symmetry. So in other words, if we have a field point up here, you see right away, a consequence of the law of edge diffraction, that there will be 2 stationary phase points. They will be on opposite sides of the reflector, and they will be in the same plane as the focus and the field point. So for axisymmetric reflectors, finding the stationary phase points is child's play. It's simply the 2 points that lie in the same plane on opposite sides of the reflector. Now this is obvious once you realize that the outline of the reflector in any plane normal to the rim tangent is the same. So the cone of rays that we normally have, as I've shown you in the previous slide, flattens out to a disk of rays. So for an axisymmetric reflector, that cone of diffraction becomes a disk of diffraction, and hence this geometry emerges. Now, if you have a non-axisymmetric reflector, such as an offset-fed reflector, or a reflector with displaced feeds, it's not so simple. Those stationary phase points can be at other locations, not necessarily in the same plane. Now, there's one other issue to keep in mind, and it's related to this issue here. When I showed you this result, I assume the field point is not on the axis of symmetry. In other words, not field points along this line here, which is the axis of symmetry. The problem is that along the axis of symmetry, for an axisymmetric reflector, there is a caustic. Recall from a previous lecture that a caustic is any point through which an infinite number of rays are expected to pass. And that's what happens for an axisymmetric reflector. On the axis, we have every point on the rim being a stationary phase point, and therefore, for every point along this line, we have an infinite number of rays passing through it. And not only do we have that in the front of the reflector, but we also have it behind the reflector. So again, every point on the rim becomes a stationary phase point, and the underlying assumption that we can reduce the integral into a discrete number of contributions becomes invalid. As a consequence, GTD, and subsequently also UTD, fail for main lobe calculation. Now this is really no problem, since we have methods such as GeoAI and physical optic surface integration that work for the main lobe. And it's a little bit ironic. GTD, UTD work for the far outside lobes, but they don't work for the main lobe, whereas these other techniques work for the main lobe, but not for the far side lobes. Now for back lobe calculation, we're still in a fix. GeoAI and POSI do not work for the back lobe. GTD and UTD also do not work for the back lobe because the back lobe lies along a caustic. This is not an easy fix, and in fact alternatives require methods that we will not talk about in either this lecture or the next lecture. Those alternatives include the physical theory of diffraction, PTD, or ECM, the equivalent currents method, which is a specific way to use equivalent currents, not exactly the equivalent currents method as I've been referring to it.